Okay, so in this video we are going to show that the integral of sec x dx is given by ln of sec x plus tan x in bracket, all right, everything plus c. So similarly, the same way we did the previous one, we're going to choose to multiply and divide by sec x tan x. Again, the reason I've chosen this is because I know that there is a relationship between this and its derivative, okay, according to this. So if I substitute this, multiply and divide this by this expression, I end up with that, okay. If I multiply that in there, I get sec squared of x plus sec x tan x, everything over that. And once again, you can tell, or you can try and see, that the numerator there is in fact the derivative of the denominator. So if I let the denominator be u, that is using u substitution, let the denominator be represented by u, and then we differentiate this. So let's quickly differentiate before we write it down. We can see that sec there, this is the same as sec is 1 over cos, so I can write cosine of x power -1, and tan, I can leave tan as it is, tan of x. The derivative here, differentiate the outside, we get -1 over cosine squared of x. Differentiate the inside, we get negative sign, so that makes this positive, and I can remove this and put sine of x, all right? Plus the derivative of tan is sec squared of x. Here I can split this up the way we did previously, and I write this as sine of x over cos of x, and multiply by 1 over cos of x. Clearly this here is tan of x, and this is sec of x, right? And then we can say this is plus sec squared of x plus sec squared of x. We can see that this expression is in fact this numerator here. So the derivative of the denominator is the numerator there. So we have the case of a function and its derivative again. So the u substitution is the reason why that u substitution works. Okay, let me just erase this so we write it neatly. Okay, so if we let u be sec x plus tan x, then du by dx gives us sine x over cos squared of x, as we've already shown. Derivative of tan x is sec squared of x, so we'll say plus sec squared of x. All right, I split this into two as previously shown by splitting the cosine into cosine times cosine. So one part we have sine over cosine, and the other one is 1 over cosine. Sine over cosine is tan, and 1 over cosine is sec. So we have sec, and the other one remains as it is. So this is sec tan times sec, right? Like that. And so I can move the dx to the other side. So du becomes that expression times dx, which is what we have up here. And therefore I can remove that expression all the way from sec squared x all the way to dx here. I can remove that and replace by du. And similarly, the denominator can be removed and be replaced by u. Same way like we did the previous one. So if we do that, what do we get? So that was our u substitution, and we've found the derivative like that. So if we substitute back into our original expression, which was this, clearly we see that the numerator is going to be du, the denominator is going to be u. Okay, so the same way that is replaced by du, the denominator is replaced by u, and if we integrate that, we get ln of u plus c. And so now all we have to do is go back and replace this u by what it stood for, which is sec x plus tan x, and we have our derivative for sec of x, okay? There will be times when we will need to put this in greater detail, but we will see that when the time comes, okay? So this is how we determine the derivative, the integral of sec of x dx, all right? Thank you very much. After this, we will look at some integrals that require the trigonometric substitution, and we will see why the integral of sec x and that of cosec x become important in these cases. Once you know these integrals, you do not need to show it all the time. So when you get to a situation where you need to find the integral of sec x, you can directly put this result. All right? Thank you. See you in the next video.